Hello physics students. This is the last of the videos for chapter 2. When we talk about falling objects, we're talking about what really is just a special case of motion with constant acceleration that we talked about in our last video. It's a special case having to do with kinematic equations. When we talk about objects that are falling, they're falling under the influence of gravity. And gravity tends to be a very constant force in at least one way. It's constant in its direction. Objects always fall towards the center of the earth. We tend to view that as down because of our frame of reference, but really, truly, it's pulling things towards the center of mass. And then when we think about this, it's important for us to recognize that although the force itself may not be constant, the acceleration created by this motion is constant. And so the acceleration created by this force is constant. And so this is a special case that physicists are particularly interested in called free fall. Now, not everything that falls is in free fall. This is a very specific physics term. It applies to things that are undergoing a very specific experience. Let's talk about what the conditions for free fall are. We're talking about objects that undergo a constant acceleration due to gravity. This implies that their velocity is changing as a result of gravity. This does not always necessarily imply that things are moving downward. Free fall could apply to objects that are moving upward, but they have to have a changing velocity that goes with a negative acceleration, because down is one of the negative directions, left, down, and backward. Things that are falling down will be experiencing a force pulling them down, and therefore their acceleration also acts downward. A very important key part of free fall is that it assumes that there's no air resistance. Now we know that this is a nice theoretical idea, but in reality it's pretty hard to get things to fall without air resistance unless you drop them in a vacuum. So things falling in space would be experiencing free fall, or in a vacuum tube. But we're going to go ahead and pretend like all of these objects that we would be working with on the Earth, a basketball or a pool ball, or things that we're using, are going to be experiencing no air resistance, or what we call negligible air resistance. Negligible is a word that just means practically almost nothing. All right, we're assuming that all these objects that are in free fall are falling near the surface of the Earth with the same constant acceleration due to gravity. What that means is that objects that are falling in space, as I mentioned before, wouldn't ideally be considered free fall because they're so far from the Earth that their acceleration doesn't match the known value that we're familiar with. And you can see those below. The known value that we use near the Earth is that gravity accelerates objects with a magnitude of almost 10 meters per second squared, or meters per second. That means that as things fall, if we rounded this to 10, that as things fall, they tend to get faster by about 10 meters per second every second they fall, as long as they're near the Earth. Pretty near the Earth would be where humans, without the assistance of any oxygen, would be able to perform an experiment. Okay, so not up at the highest top of the highest peak, not up in an airplane, not in the space shuttle, certainly not up at the space station or on the moon. Just near the Earth, what we generally consider the normal place where humans are doing these kinds of experiments. So again, back to this. Here's the symbol. We use a special symbol. Instead of using acceleration in the y direction, which is what you would normally use for things that are falling, we're going to use a special symbol, little g. Little g, that's its street name. All right? The acceleration of gravity near the Earth. And this is about 10 meters per second squared. So that means if I drop something from rest, after 1 second I would expect it to be going downward at 10 meters per second. And after 2 seconds I would expect it to be going downward at 20 meters per second. I'm rounding. After 3 seconds I would expect it to have sped up to about 30 meters per second, and then 40 after another second, and 50, getting faster by 10 meters per second every second that it falls. But it could also mean that an object is getting 10 meters per second slower every second that it moves upward against gravity. And this is often one of the things that throws people off with free fall. It could mean that something is moving upward but slowing down at this rate. Okay, so those are some of the basic assumptions for understanding free fall. Often what we'll tell you is to go ahead and round that to 10 meters per second squared. If we don't tell you to do that, then you need to use 9.81. Also, this is an acceleration, which means it's a vector. That means it does have a direction. We should always assume that it's actually going to be negative 9.81 meters per second squared. The negative means that gravity should always be acting down from any good normal human frame of reference. Okay, so let's take a look at an object that's in free fall. Let's imagine that we took a billiard ball and we threw it up into the air, straight up. So this path is linear, it goes straight up and then reaches its highest point, stops, and turns around and comes straight down. Well, this object is in free fall, not just when it's falling down, but also when it's on its way up. The reason why we know this is true is because its acceleration is the same, whether it's moving up or moving down, although its velocity is quite different. Take a look at the graph here. You can see that this is a velocity versus time graph. It's telling us how fast, that's its speed, and in which direction it's moving, up or down, based on positive, these numbers here are all positive, or negative for its direction. So you can see here these numbers are all negative. So that means that initially, it looks to me like initially this object started moving upward at about 11 meters per second. So that's maybe here when it first leaves the hand of the person who threw it. Of course, this implies that we didn't really start paying attention until the moment it left the person's hand and was actually in the air. One of the important things that you need to understand about free fall objects, and this wasn't on the previous slide, is that there can really be no other force acting on it but the force of gravity, which means it can't be experiencing any other outside acceleration. So as long as it's touching that person's hand, it's not in free fall until the moment it comes off their hand. And that is going to be its initial velocity. And here we can see its initial velocity is upward. Because its initial velocity is upward, we would expect that to be a positive number, because positive y is going to be up. So the upward is always a positive direction. So sure enough, here we see it starts out positive. But what we know is that the entire time that the object is moving upward, gravity is acting to push it downward the whole time. So here we have a force that's producing an acceleration in the negative direction. We can think back to when we first talked about acceleration. If you have an object that's experiencing a positive velocity but a negative acceleration, that object is going to be slowing down. Consult the table in your chapter. A positive velocity and a negative acceleration is going to produce an object that's slowing down. And so we would expect an object that we toss straight up in the air would in fact be slowing down. And that's what we see going on here. As we look at the graph, we can see that it goes at a certain point. When it first started at time 0, it was about 11 meters per second. And here we can see by 0.25 it appears to be closer to 8. And here we can see that after half a second it appears to be closer to 6 meters per second. But still positive, still moving up, but slowing down. And here we can see after 0.75 seconds, it's closer to maybe about 4 meters per second. And after 1 second, it practically has no velocity at all. Until we see that at this point right here, point B, its instantaneous velocity at that moment is actually 0 meters per second. The ball has stopped. It's not moving at that point. It's reached what's called its apogee, or sometimes it's called its apex for things that are moving linearly. So it's reached its highest point, its apogee. And that means that from that moment on, it's going to no longer continue moving up, but now it's moving down. So after that, we see that the velocity is going to be in the negative direction. It's going to be moving downward. But its acceleration is unchanged. Its acceleration, gravity is still pushing it down. Now we have something that's experiencing a negative velocity and a negative acceleration. And what we know about those objects, by consulting that chart when we talked about acceleration, is that objects that have both a negative velocity and a negative acceleration will be speeding up. Is that what we see in the graph? Absolutely. We can see that from this point on, that after 1.5 seconds, it has a velocity of -4, and after 2 seconds, it appears to have a velocity of maybe -8, and so on and so forth. What we see is that the magnitude of those numbers is getting bigger, and the sign, negative, which indicates its direction, has just changed is all. So it went from 0 to 4, went from 0 to 4 to 8. Yeah, that object's speeding up. It's speeding up as it falls. So what we can see is that by the time it gets to point C, that it actually has increased in speed. And its velocity is well documented here on this graph. Well, remember, this is a velocity time graph. And the slope of a velocity time graph is going to give you the acceleration of the object. You can see here that this slope, the slope of a graph, is going to be its rise over its run. And here we can see that its rise is actually a drop, and its run is in a positive direction. So we can see that we've got a negative rise over a positive run. That means the slope is going to be a negative number. In fact, I think you'll see, if you check it out, that the slope is going to be -9.81 meters per second squared, because this object is being accelerated at that rate. So the slope of this graph should be about -10, rise over run. So again, just to recap, on the way up, the velocity decreases until the ball reaches its maximum height, also known as its apogee. At that point, it stops, its velocity is 0, and the ball changes direction. It's not possible for an object to change direction without first stopping. On the way back down, its velocity increases, and for the whole path, its acceleration is a constant, -9.81 meters per second, due to the force of gravity. Don't confuse the force of gravity with the acceleration of gravity. The acceleration of gravity is always 9.81 meters per second squared downward on this planet. However, it is going to produce different forces based on the mass of the object, something we'll discuss in a later chapter. Also keep in mind that if you went to a different planet where all these assumptions weren't true, then you would not be assured that the acceleration of gravity, the free fall acceleration, little g, would be -9.81 meters per second squared. If you were on a different planet, if there was a thicker atmosphere there so that you couldn't disregard the air resistance, if you actually did an experimental laboratory test to see if things do actually accelerate at this rate, there's really air in this room, so that would produce a slight variation as well. But for calculating theoretical problems that are free fall problems, this is the way to go. So what do? Well, because gravity is a constant acceleration, we can use the kinematics. The only thing we're going to do here, though, is when we rewrite these kinematics to account for free fall, we've done a few things. Take those same 4 kinematics that we talked about in our last video, and these 2 changes are made. Because we know we're talking about something that's falling, we're going to change all of our position data from x to y. Remember, those equations said delta x equals 1/2 v initial plus v final times t. Here we've used delta y. And that's because we know the object's displacement is going to be either up or down. And the other thing is, again, instead of using a for acceleration, you can see that we're going to use g for acceleration, indicating that we realize that we're in a free fall situation.